I have been working in recommender system already for 10 years. And since I finished my PhD and started building my research group in Chile, I have really grateful of having very good students, master students, PhD student, undergrads. At some point we say, okay, let's prepare a tutorial on some topic that we have been doing research in the latest years. And it was the opportunity to do it. So here, let me introduce the tutorial on visual recommender systems with deep learning methods. We are going to have a few aspects of theoretical that we are going to present in a slide, but not too deep. And we are going to focus on the presenting code and also sharing a bit how to use PyTorch in this session. There is a lot of content. We only have 3 hours, but we are going to share all the material, slides, Google Notebooks, code, data in the repository that for this in github.com. So you will be able to practice on your own and maybe create your own method based on this initial build that can be bootstrapping. Okay. So let me introduce people. We have here Antonio Osa, well, Dennis Parra, myself here, a professor in the computer science department in Catholic University of Chile. Antonio Osa, who's there also in the list of participants in Zoom, master student at PUC, Manuel Cartagena too, Patricio Cerda, who recently graduated. So he's an alumni, and also he works as an engineer, AI engineer in MindsDB. And Felipe del Rio, who is right now a PhD student in our program. So these slides are right now in the website, and this is the URL, github.com, ialab. Like -PUC Visual Rexis tutorial. And here you will be able to find everything, models, data, slides. So you can follow on later on. I also want to take this opportunity to announce a new website for the group on human-centered AI and visualization. You can check it later. And let me tell you then what this tutorial is about. So we are going to have 5 sessions. In the first one, I'm going to introduce this visual Rexis and the main models that we're going to use for feature extraction with convolutional neural networks and also the idea of data sets. So then, having this initial introduction and some initial definitions, we are going to give the token to Antonio, who is going to talk about the pipeline that we built for training and testing visual recommender system in PyTorch. And he will show an application with 2 of the initial models, VisRec and Visual Bpr. Then we're going to have a break. And after the break, we are going to go in 3 sessions, 1 per each method. The first one, dynamic visual Bpr. The second one, the session number 4, CuratorNet, which is a method that we developed and we introduced the last year in the Recommender System Conference. And session 5, we will talk about attentive collaborative filtering, which is very interesting because since it has attention, you can also have some type of explanations when you produce recommendations, right? Then only a small break, and then just 5 minutes to make a few remarks to finish this tutorial. So in the session that I'm starting now, I'm going to talk about recommender systems, visual recommender systems, some motivation and applications, some ideas of manual engineer visual features, how the creation of features started in this field, in computer vision. Then I'm going to talk about these 3 deep neural networks. There are many more, but these are very popular and are the ones that we are going to use through the tutorial: Alexnet, VGG, and ResNet. Then I'm going to just have a small content related to transfer learning and how this is useful for visual recommender systems. And then I'm going to talk about data sets in this area to finally, in this session, have the first hands-on session with a Google Notebook, where we can see how to extract visual features with these models and do some very simple operations. Yeah. Okay. So you have seen this probably for a long time already. What are recommender systems? These are systems that help individuals or groups of people to find relevant items in a crowded item or information space. This is a definition by Sean McNee in 2006. And Robin Bird added in a personalized way. This was in a few years later. So when we talk about recommendation system, there are many surveys for already more than 20 years. And some of them, they talk about classifying them. The first methods obviously were related to this notion of co-occurrence of consumption, and that is the family called collaborative filtering. Many of the methods related to user-based and item-based collaborative filtering, matrix factorization are based on that. But there is also content-based filtering, right? And when recommender system started, content was mostly text. For instance, someone liked a book or a content, and we could represent the content of that item and maybe have some inference of similarity. And hybrid methods were just mixes of these two different approaches. But there is another classification, maybe more similar to the area of data mining or machine learning, where we talk about memory-based models, where we don't store a synthesized model. We actually have the instances. And then when we want to make a classification, or in this case, a recommendation, we use the actual instance representation that we have, like in user KNN or item KNN collaborative filtering. And in the case of model-based, we want to build a more concise model of users or of items. And in this way, then we can make recommendations later. So in this tutorial, we're going to focus on content-based filtering and hybrid methods. And of course, the content is visual content, right? And model-based, because we are actually building representations thanks to deep neural networks of these items and users. And with this information, then we can produce recommendations. I don't know if there are any questions at this point. At any point, you can just write and open your microphone and make any question. We are very open to discuss during the presentation. Okay, so the motivation first is that as the web and the internet was developing, we started to see a lot more content, especially at the beginning with social networks like Facebook and Twitter. But that content initially was mainly text. And from 2010, more or less, we started to see services dedicated mostly exclusively to visual information, such as Pinterest, like just image boards and videos, right? Instagram, and more recently, TikTok. So this is actually using the bandwidth of the internet right now. Like there was a point in which it was mostly text, and then we started to have mostly multimedia content. And the other aspect of this is that e-commerce started to use a lot more multimedia content, like fashion, e-commerce, tourism, real estate. We have the case of Zalando, for instance, or Go Places, well, Amazon, of course. I don't know, Airbnb, which have images, and then these images can also be used as a means to get information about the users and also to make recommendations. And well, one important event in all this is the development of deep neural networks, which means the increasing performance of visual features that were obtained from these deep neural networks starting in 2012, and the growing potential of transfer learning. So then we can use these features that were learned in a different task, and then we can move them to, for instance, recommendation ranking, because mostly these initial models were used for classification. So to recap a bit of history regarding the data sets in computer vision, we can see that in the 90s, there were some data sets like MNIST, or Faces and Card, that were of the order of, I don't know, tens of thousands images with different categories. And this grew a lot, not a lot, but a little on the 2000s, like the Caltech 101 and the Pascal book with several classes. But it wasn't really like a huge data set, right? And this changed with the ImageNet challenge in dataset that Professor Fei-Fei Li now at Stanford led. And so they crowdsource images and the annotations, right? Right now, this dataset has close to 15 million images with close to 22,000 categories, right? And where are these categories coming from? A psychologist called Miller, he started a project in 1980 in Princeton. And what he did is like to start words, concepts, and then trying to create like a taxonomy, an ontology of different concepts. And it was called WordNet. Was a lot used in NLP, natural language processing. But then Professor Fei-Fei Li said, okay, I want this concept, but with images. So these were the labels that she was interested in filling with images. And this process was performed for a long time. It took the initial version of ImageNet 2.5 years. It was conducted with Turkers in Amazon Mechanical Turk. And originally, it had 3.2 million images from a bit more than 5,000 categories. But as you can see, this was a lot more than the largest data set that was at that point. So having a lot of data, labeled data, having better hardware like GPUs, and having better algorithm to train, it finally produced the like an event that actually happened in 2012. There was this ImageNet challenge that where people around the world competing to classify and images and detect objects. And in 2012, a team from the University of Toronto, led by Professor Hinton, got an error rate below 25%, which was a 10.8 point margin, and it was 41% better than the next model. And this was the point in which all the companies and most people started saying, okay, we have something here. Maybe we didn't care too much about neural networks, but these deep neural networks are really going to have a big impact in vision. And then we started to see it in other areas like natural language processing. So what you see here is a plot in which we see how the error of these models start to decrease like very, very quickly over time. And the red line shows the performance, the error rate of a human, of an annotator. That is around 5%. And we saw for the first time in 2015, a deep learning model which error rate was even smaller than that of a human. Of course, we cannot say that we have already accomplished like general artificial intelligence, but then we have seen tasks in which, with the help of these models, we are really having better performance than what we can expect from humans. And there is another aspect that is probably the most relevant here, which is that deep learning makes a revolution not only in performance, but also in the way that we represent things. So in the past, we had this, well, let me use this annotation tools here. Here, we have what was happening in the past, right? In several fields. We had input data, someone who was doing feature engineering, trying to understand, okay, what features can we get from here? Maybe we can get light, maybe we can get colors, histograms of certain, I don't know, patterns, and then we give it to a traditional machine learning algorithm. And deep learning somehow skips this intermediate model in which you have to actually provide the feature engineering manually, and the model does both the task of, let's say, classifying, and at the same time learning the features automatically. This was very, very important because if we see the history in computer vision, we saw a lot of people doing big efforts and with very good performance, like local binary patterns, a histogram of oriented gradients of the shift features, right? But someone thought of that, thought, okay, maybe we can get this type of pattern. And in the case of the, for instance, this first neural network, the Alexnet, we saw that the model, whose goal was, okay, let's have an image input, let's have a classification after this fully connected layer 7. What we're going to have now is just the representation learned. And then after I have trained this model, what I'm going to do is I'm going to take any other image, maybe which was not in the original ImageNet dataset, and I'm going to do a forward pass through this deep neural network, and I'm going to output this fully connected layer 6, and I'm going to use it as a representation of the input image, right? And this started to change how we can use this. Well, this network has about 60 million parameters, which is a lot, because of course, to train a model with such number of parameters, you need a lot of data. That's why the 3.2 million images were necessary with the labels. But then we started seeing progress. Let's see, we could see then, for instance, the VGG that was introduced by the Visual Geometry Group at the Oxford University. And what they did first was trying to build an even deeper neural network by reducing the number of filters. The Alexnet has all big and small filters, like boxes of, I don't know, 11 by 11. And in this case, they only use small filters, but they increase the depth of the network. Here you have 138 million parameters, but much better performance. And you can just reduce or increase the number of layers, and this might have an effect in the model. And then even later on, we saw the ResNet. The ResNet architecture introduced this residual connection, right? So we see here a diagram with VGG, with a model with like the VGG, but with 34 layers. And here in this row, we see the ResNet, where we have 34 layers, but we have residual connection, which allows you to propagate the error in deeper layers, right? And here on the left, we see a table with results, and we can see that the larger the number is, the larger the number of layers. And we see an error in the top 5 error category of 4.49, which is smaller than the previous networks. There are a lot of other networks like Google Net, Inception, then there were combinations of this. But with this, we can have an idea of how quickly this field has been progressing in the latest years. So I would like to ask you guys if you have any questions so far. No questions? Manuel, do you see any question in the WUVA or no?
Not yet.
Okay. Then, how are you in terms of time? 25 minutes. I'm good. Okay. So then we even saw that not only people were trying to to devise the architecture of the network, they were trying to automate how to find certain components of this network. And that's how we saw this network called NASNet, yeah, which is like a network architecture search. And actually, it had better performance in the ImageNet challenge compared to ResNet and combinations of other networks. But there was this research called Do Better ImageNet Models Transfer Better. So if we can say that having the top result in ImageNet like necessarily means that we are going to have better representation for other tasks. And the answer was not, because we could see that without the fine-tuning, ResNet, despite not having better results than NASNet, was having better results for transfer learning. So we were really motivated by this result, and we did this first analysis in which we used these representations, ResNet 50, VGG 19, NASNet, Inception ResNet, and a random, to make recommendations and evaluate them with the typical traditional recommender system metrics. And also, we were evaluating the performance in the ImageNet challenge. So this was interesting because we see no correlation. On the one side, we see that the top performance in the transfer learning setting for recommendation was ResNet and BGE, but in the ImageNet, the top performance is actually from NASNet and from Inception ResNet. So maybe you can start like somehow overfitting these data sets, but you are not necessarily doing better transfer learning for other tasks. That's quite important to remember. Okay, so we have been talking about the different architectures, and now what about recommender systems, right? So one thing is that in the recommender systems area, we sometimes complain that there are like always the same data set, but there are some benchmarks. We have, for instance, the movie lens dataset. We have the Netflix dataset. There is also Last.fm dataset, right? But when we talk about visual recommender system and we want to have like a typical transactions, right? User, item, or rating, timestamp, something like this. Maybe we can find something like this in some repositories, but usually they don't share the images because the images are collected from some portal, some web commerce, and they don't have the rights. So then what we get are embeddings, the embedding of the image. But if we want to check if the image recommended is good or not, we don't know. We just can see the embedding, right? So if you ask me if there is something like the movie lens dataset for visual recommendation, sadly, there is no such a thing so far. So there are some datasets, but usually you find embeddings as NumPy files. Or sometimes you get some files with the URL of the images. So you then have to start on your own collecting these images. And in some cases, these images are not available anymore, right? They are not necessarily like always present there in the link. So, well, you can still find this is a great repository of Professor Julian Macaulay from University of California, San Diego. He has the dataset of Behance and Amazon, but you have to collect the images on your own. And there is also this dataset of Pinterest, but also you actually download a MongoDB dataset, and the images, you have to start scraping them. Yeah. And we ourselves, we produce this dataset of UGallery, which is art, an e-commerce art website, but we also provide only the embeddings because we don't have the rights for sharing the images. So we have developed the Wikimedia Commons dataset. The Wikipedia website that we all know, they also have other type of projects. One of them is Wikimedia. And in Wikimedia, people, if they own a picture, they can share it. And when they share it to the portal, there is like a voting in the community. So every time someone say, hey, I want to share my picture with the Wikimedia community, then people start saying, okay, I want to vote. I think that this is a good picture. And other people say, no, this is a bad picture. They do this with every image that people share there. So then we have the option of having an item, and we have votings. Maybe they are not actually voting for their preference on the image, but on the quality of the image. But there is also probably some sort of a signal related to preference, right? And this is the data set we collected with the help of Diego Saez, who is a researcher who works in Wikimedia Foundation. And it's not very large, but the nice thing is that we have embeddings, and we also have the images. We can share the images. So you guys can actually take this on your models. You can build your own embeddings. You can use also our embeddings, and you can explore the images, conduct a user study. You're really going to have a great time enjoying the data, right? So then we have a bit more than 1,000 unique users. We have a bit more than 9,000 unique items. And in this data set, we have close to 100,000 interactions. Here you see the distribution of interactions per item and per user. And here is an example of an image that someone uploaded. And here are the votes. You can find this actually in the portal of the Wikimedia Foundation, right? Okay, so we can now have the coding session. I don't know if there is any questions so far.
Not yet, Dennis.
Okay, let's have a little 1 minute break. Maybe someone wants to ask or comment something. Okay, just to follow on a bit, we have talked about the models, and mostly for deep learning, the motivation of why we want to use these deep learning models of computer vision for recommender systems. And now the tutorial that we are going to see next is available on the website, on the github.com website of this tutorial. And what we are going to do is to load some Wikimedia images. We are going to get features from these models that I described already: Alexnet, BGG16, ResNet 18, and NASNet. And then we are going to see what are the representations and what would be more or less some simple operations that we can do with them, okay? And here you see the link to the session. Okay, let's go. Here. Okay, right now you should be seeing the tutorial. Is that right? Yes. Do you see
Yes,
the
Dennis.
Google Colab? Yeah?
Yes, yeah.
Okay. Thank you, Manuel. So here, well, just to make sure that you can get to this later, if you go to the website of our tutorial, you go to Colab Notebooks, and in Colab Notebooks, you will see a list of Google Colab Notebooks, and you can click on the link of Visual Feature Extraction. This is the one I'm going to be showing right now. Okay, so the first thing that we do is to call just this line to download the data that we have, which are these files, image files, right? It might take some time depending on my network speed. I hope it just might take a few seconds here. Okay, then with the it's taken some time, but here I also have the outputs of this notebook, so I can continue showing this. Then here I can unzip this, and in your, maybe some of you are familiar already with Google Colab. If you are not, this is like a Jupyter notebook that is available online, and it's really useful because then all the infrastructure, all the memory, hard disk, GPU, CPUs is already there in the cloud, right? And if I click here in this folder, I can see the folder Wikimedia Rexes, right? So I already know, okay, the data is here, right? I'm going to just set this variable, and I'm going to change to make sure that I have the number of images. Here I have 4,969 images. Then we are going to import the libraries to execute, mostly NumPy, many related to Torch and Torch Vision, and also Pil and Matplotlib in order to show the images that we'll describe later. This is just a line in case that there are some files which might be too large, and we don't want the Pil library to crash when there are some files that are too large images. And this is just to parse the different files that we have within the folder of Wikimedia Rexes, and then store them in this array data. So we are going to have the image and also the image path. And this might take a few seconds, but should be quick. Then we are going to be able to get the images there in our array. So the next thing we want to do is to maybe analyze some of these images if they're if they are correctly being displayed. Maybe, I don't know, the zip file was corrupted or something. So we define this function display images. I'm just going to load it. And with this, I'm sampling images and I'm showing them. So you can see these are the type of images that we will see. Photograph pictures of very different nature, like images of animals, buildings. Sometimes you have, I don't know, like house objects, like still life type of things. Quite different. This is just to give an example, right? Sculptures, etc. Okay, so I'm going just to save in my mind some of these numbers because I can use them later to test certain things. For instance, 2460. I see a little insect there on a green background. Okay, so now we have the images files, but what we want to do is to get the features that we can obtain from a neural network. Now, training these neural networks can take several hours. So we are not going to do this during the tutorial. So what we are going to do is to use a neural network which is already trained. So the parameters of this network are already fixed. But we are going to use it to input an image and then obtain as an output the features. And those features we can use them for search, recommendation, or for many other tasks. So this class here, feature structure, is a generic class that then we can provide it with different models like Alexnet, VGG, ResNet to extract the features from this pre-trained model. So let's start with the Alexnet, which is this initial neural network that Hinton used in the ImageNet challenge, where they had this breakthrough result. So as you see, this is as simple as models.Alexnet, right? But what I'm loading here, which is very fast, is like the architecture, right? So I can see here convolution, ReLU, which is like rectified linear unit, the size of the kernels, the size of the strides. So these are the operations that are going to be happening in the network. And I have, for instance, here a final linear layer who is going to, I don't know, output classification, right? So then I'm going to use this feature structure on this models.alexnet. But in this block, I'm going to actually download the Alexnet model and the weights. How are we on time, Antonio? Are we good?
Yeah, no problem. We have, I think.
Okay, I think.
Yeah, okay.
I think I'm gonna show just one example, so then I'll give you your 40 minutes, so you have enough time to explain. Okay, so I'm going to show this example only with one network, but you will see in the notebook that you can do exactly the same with the other networks, ResNet, BGG, etc. So this might take some time because, as you see, it has to download from PyTorch the model, and then I'm going to close this. Then what can I do? Because now I have the actual model. And I have actually input the each image through the model, then I have the features, right? So now what I can do is to define this method that is going to, given an image, is going to give me the most similar images based on the features from the neural network, right? So here we're going to pick randomly one image. Well, actually, I chosen one. And we can see the closest images doing cosine similarity on the Alexnet features, right? And we can play with many of them. Actually, as I was saying before, from this random sample, I'm going to get this 2460. That's the ID, the IDX. And I'm going to add this here, 2460. Play button. And I have that, and here are the closest one. So as you see, there are some. Here they are in love. And here I see other images which are similar, but it's not exactly the same type. What I wanted to show is that when you use the other networks like BGG and ResNet, you have a lot better results in terms of similarity, right? Because of the improvements of those. But you can do it on yourself later. Here are even the citations. You just have to play that button. Here we also have the Alexnet, the mobile version. And at the very end, there is this form so you can do it more easily. You can just click, write a number here between 0 and 1096, choose the model, choose the number of closest neighbors, and then you can obtain something like the things I'm showing here, right? Okay, so as we can see, it's quite easy with the current implementation of PyTorch to just load a model, load a data set, and obtain features. Now, how can we use this actually to evaluate and to build recommendation systems like the ones that we read in the papers? That aspect is going to be now addressed by Antonio. So now Antonio is to be presenting the next slides and also the demonstration of the first actual recommender model, VisRec and Visual Bpr. Okay. So Antonio, I'm going to stop sharing and then you follow.
Okay. Like Dennis said, I am Antonio Osa, a master's student working in recommendation systems and explainable AI with Dennis and another advisor, Cancel Lowell. And what I'm going to show you now is the pipeline that we've developed to run our experiments. This includes code that I developed for my master's thesis, but now has been further improved by the team that is presenting the tutorial today. In particular, in this part of the presentation is composed of 3 parts. The first one being the pipeline. Then I present VisRec, our first baseline model, and then Visual Bpr, the first deep learning model. So let's start with the pipeline. First of all, I'll present the general structure of our pipeline, which can be easily identified in our repository. Then I'll dive into the details of each of these stages of our pipeline. And finally, I'll add some tips and recommendations in case that you want to use our pipeline with your own models or dataset. Okay. This diagram represents the 3 stages of our pipeline. The first one being data preparation, composed of 2 steps. The first one is data analysis and data formatting. I'll explain both later. Then we have the model training with 3 steps. The first one being building and embedding using what Dennis already presented, and also creating the training triples. And then we have the actual model training. And finally, we have the model evaluation, where we use our trained model to calculate metrics and easily compare results across data sets and models. Okay, our repository is organized with the following folders that you can see now in GitHub. The first one is the checkpoints, where we store the trained model weights. At the moment it's empty, but the pipeline assumes that that folder exists. So that's why that's already uploaded. Then we have also the data folder, where we store and manage our data. Colab Notebooks contains the links to our Jupyters in Google Collaboratory. And then we have data sets, which contains the PyTorch specific objects to train our models. The models folder contains the model implementations, which you'll see later in the tutorial. The trainers folder contains the training loops for each of our models. And finally, the utils folder contains the code that does not belong to any of the other folders. In our repository, you'll also find our Jupyter notebooks, which implements at least one of the steps of our pipeline. So for example, the number 3 with Bpr is the model that I'm going to show you, and that contains the training stage. Okay, so let's begin with the data preparation stage. As I said, this stage has 2 steps. The first one being data analysis, something that will not be deeply covered in this tutorial, but we have a small and simple example in our repository for you to see in the data folder. But first of all, I want to mention an important step in our pipeline, well, in any data pipeline, that's splitting the data in training and test sets. Traditionally, in a recommendation setting, the item that we use to evaluate our model or to test the model is the last item which the user interacted with. So for example, we have a user model 1 interacted with 2 items. So we leave the last one outside of the training loop, and we only use it to calculate metrics. And the first one is going to be used in the training loop. In the case of the data that we're going to be seeing today, we already split the data set, so you don't have to bother with that. Okay, so the data analysis is a useful step to gain insights about our data that can be useful for training. For example, at the right, you can see one of the plots that shows the number of interactions that each of the items have. So, for example, we can easily see that practically all the items have at least 5 interactions. So we're not in a cold start setting, meaning that almost all the items have already been consumed by one of the users. Okay, another important step is the data formatting, which is a key component in our pipeline, because to be able to expand our pipeline and to try out different data sets, we define a specific structure to don't have to change the code further into the pipeline. So for example, we're going to be using the Wikimedia dataset, so we're always going to need this structure, user ID, item ID, the timestamp of the interaction, and a Boolean column showing if the interaction is going to be in evaluation or training. So in case that you want to use your own dataset, you need to follow this structure using the same column names, sorting the interactions by timestamp, and correctly using the last column. And we'll also be using the next step is building and embedding, something that Dennis already commented. So what we do here is feed each of the images in our dataset through a pre-trained model, for example, Alexnet, and store the output of normally the penultimate layer as a vectorial representation of the item. We store this representation in a NumPy array with this structure, a table with the item ID and the vectorial representation. We store those in a NumPy file, and later we just load it to avoid calculating these weights each time. Before entering the details of the training stage, in a recommendation task, we can take any of those 2 approaches. There are a few more, but the most popular are this one. So a point-wise approach means that we look one item at a time, and we try to predict or learn what's the rating that the user assigns to that item. And we also have a pairwise approach, where we try to learn the optimal ordering between pairs of items. So the common notation for a rating that we're trying to predict for a user and an item is using this letter. but we're going to be using this approach, using 2 items at a time and trying to learn the optimal ordering using implicit feedback. As we're going to be using the pairwise approach, we'll be using Bpr, which is Bayesian personalized ranking, which is a training strategy that was published years ago, but it's a training strategy that is really popular now. And in fact, all of the models that we'll see today use Bpr for training. Okay, so something that we need to train our models is creating triples. This means a triple with user, positive item, and negative item. So we store those in this format using profile, the history of items consumed by the user, the positive item, the negative item, and the user identifier in case we need it for our models. For this task, we generated 5 million triples using the implicit feedback node, and we also generated 500,000 to validate our models. In the case of the evaluation stage, we use a different file because we need the ground truth, or the item that the user actually consumed at the end of his history of interactions. And that's the format that we use for that file. But all our scripts leave the output in that format and also assume that format when the file is required. Okay, so in the actual training procedure, we use as input the embedding file, the NumPy file that I already mentioned, and the triples file, the CSV that we just saw. Then we have the actual model training that it's already implemented in the Jupyters that you can see in our repository. And the output of this stage is a model checkpoint, which is a file with the model weights that were learned during this process and can be easily loaded later when we need it for the evaluation stage. An important difference between the training and the inference of the models, that means when we try to generate recommendations or try to create predictions, while we're training using Bpr, we need 2 items because we want the model to learn that the score or prediction for the positive item must be greater than the prediction for the negative item. So we want this value to be positive as we can. But when we're trying to do inference or recommendations, we only have 1 item. So we only calculate one of those terms. And you'll see in the code later where that difference happens. What I'm showing here is the model evaluation loop. In this stage, we just load one of the checkpoints that we already trained. And we do three things for each user. We predict the score for each of the items. Then we sort those scores and try to generate the recommendation list. And with that list, we can calculate metrics, which I'm going to explain later. And all of those metrics are already implemented in a model in the repository. In case that you want to use our pipeline with this same data set or another, one of the main requirements is, of course, using a GPU, but Google Collaboratory helps a lot. In fact, works really well with the contents of this tutorial. In case you're using a different recommendation task, you need to define an explicit criteria to label the rows that you'll be using for the evaluation step. Also, please follow the format that our files use. And something really important that we're going to be doing right now is using a simple baseline. Okay. If you add your own model implementation. If you follow the structure that's already presented in the repository, you should have no problems. And we also documented the repository in case that you want to add a different data set or you want to add another model. Okay, so now the second part of this session is going to be about VisRec. I'm going to explain right now what it is. Okay, so VisRec was presented in this paper, but the main focus on this paper is another model that will be presented later, into the tutorial. VisRec is actually used as a simple baseline, and that's why we're interested in that model. So what's the context of the creation of VisRec? We wanted to define a simple and performant baseline model to calculate similarity between user and items, trying to recommend, of course, the items that are more similar to a user representation. And this model is said to be a nearest neighbor style recommendation, and you'll see later why. And the images are ranked according to their average distance to the user items, meaning that we want to recommend the items that are more similar to the user. Okay, so here's the intuition. Imagine that we have a user that has already consumed 2 items, which can be seen here. But we want to generate recommendations for that user. So we have this other set of items. How can we calculate the similarity between each of the items and the items that the user has already consumed? We have different strategies. For example, we will use the maximum score. In this case, we stay with 0.5, or we will also average the distance between each item and each of the items that the user consumed. In fact, those 2 are possible options. The code implementation contains both, contains those 3 options, the maximum, average, and average top K. And VisRec calculates the cosine similarity between a pair of items or user items using that formula. So for example, we can, in the first strategy, the score of an item is the maximum score or the maximum similarity value with one of the items of the user history or consume items. Okay, in this tutorial, we'll use the same metrics because we want to data models. We want to compare our models using the same dataset. So we use 5 offline metrics. The first one being AUC, which can be understood as the proportion of correctly predicted pair of items. Remember that we're learning the optimal ordering, and that value over the total of predictions that we try to make. And also we have a mean reciprocal rank, which tries to show how well we rank the first relevant, actually relevant item. And we also have some more traditional metrics, precision at K, recall, and NDCG. All of those formulas will stay in the presentation that will be submitted later after the tutorial. Okay, so the VisRec implementation is already published in the repository. For the sake of time, I won't be showing you now the code, but it's available. You can just open the Jupyter notebook and run the code. In fact, you don't even need a GPU for this model because it's not a deep learning model, and it's really, really fast. So VisRec will be our baseline. It provides a reasonable result in AUC. This metric goes from 0 to 1, and 0.5 is a random recommender. So 0.6 is a good baseline value. Also, we noticed that VisRec obtained good mean reciprocal rank and also NDCG values. And well, later you'll see the other models to know how good was our baseline. Okay, so now we're going into the last part of this session, which is the first deep learning model, visual Bpr. Okay, visual Bpr was presented in this paper from 2015. Is a deep learning model that tries to embed information from the visual information from the items into their predictions. So instead of being a simple approach using, for example, matrix factorization or something like that, we can also feed our model with visual information. We'll now see how they do that. Okay, so as I said, previous work did not consider the visual appearance of the items. So that there was a content-based approach that could be useful in this task. And also the modeling of the visual Bpr was derived from Bpr. And the idea was to exploit the not only the latent information in the interaction, but also the information in the visual factors and how the user reacted to those visual factors. And this is a useful approach in a causal problem because our score or prediction does not only rely in the interactions between the users and the items, but also on the item appearance. So that is can be a huge boost for items that are newer in our dataset. Some of the key insights or something that we should consider is that visual Bpr uses a pre-trained network. In fact, they use the Alexnet network to generate an embedding, just like we do in our pipeline, to represent each of the items in the dataset. And the preference predictor is a bit of a complex formula that tries to model a lot of things, but we're gonna explain that right now. Okay, so this is the preference predictor of the visual Bpr model. It has a lot of terms, but each one has a purpose. The first one is a global offset, and then we have the user bias and item bias. All those three values are scalars. And then we have the first latent component, which tries to model the compatibility between the user and the item. This value does not use any of the visual information because the visual information is used here. So this term tries to model the visual factors. In fact, tries to model the user preference over the visual dimensions of the items. And something that they did in the paper was, instead of feeding the complete embedding and using the full vector, they let the model learn a transformation to reduce the dimensions of the embedding. So instead of working with vectors from like 2000 values, we let the model learn a transformation to go from 2000 to 100. So our representations are smaller and can contain the most contain more important values. And finally, we have an important term, which is the user's visual bias, which is the overall opinion of the users over the visual representation of the item. So that part is not personalized, but global. Okay, but as I said, we're using a pairwise approach. So that means that we are seeing two models at a time, a positive and a negative item. And that means that by using the same equation that I explained before, we can cancel some of the values. So for example, the global offset will be the same in any pair of items, and the user bias will be the same, assuming that we're always recommending for the same user. So those two values can be canceled. Okay, how does this look in our code? Well, you can find the model implementation in that route in the model folder, the file named Bpr. You can identify each of the terms in our code. So for example, this method is the model initialization. And we here define what are the layers or embedding that we need in our models. And this is the forward pass of the models, where we actually pass the input in our training stage. So as you can see, we use the user item, user ID, positive item, and negative item. So for example, to calculate the user biases, we have an embedding here to contain that vector and that matrix. And we load those values, and then we generate the prediction using the positive item and the negative item. We also have the same for the latent factors. We have an embedding for those, and we load the information when we are training the model. And again, all of this is used to generate the output of the forward pass. We also have we also use here the visual information. So as I said, we not only use the item features which were represented in our embedding, but we also learn another embedding to reduce the dimensions of the first one. And in the forward pass, we reduce the dimensions using matrix multiplication, a term that is present here. And we also have the user's visual bias, the last term that I presented before. And we calculate and we also add the term to the output of the model.
Antonio?
Yeah.
I see a question in the chat from Luis. He says,
okay.
How are the positive and negative item pairs selected? Is it all combinations? If you can answer that.
Okay. So I'm gonna. Okay. That happens in this stage where we create the attributes for training. What we use is a naive approach, meaning that we take, for a single user, we take each of the items that the user has consumed. So we have the user ID, we have the positive item, but where does the negative item come from? The negative item, this is a naive approach, so it's very simple. We take any item that the user has not consumed. So that's a random selection from all the data set. Any item that the user has not consumed, we say that is less preferable than an item that the user already consumed. I hope that answers the question. Great.
Yeah, you say thanks there.
Yeah,
great.
perfect.
Thank you.
Yeah, I was here. Yeah. So in the code, the variables are, the code is, we try to use the same vocabulary as in the paper. So you can follow the implementation really easily and add modifications if you want. And as I said before, while we are training our models, we do not calculate the same value as in the inference stage, in this case, when we're recommending. So for example, this is the training step. We calculate this term using a positive and a negative item. But when we're recommending, we only use one of the items. So it's a simple formula. In fact, it's the first preference predictor that I presented. And again, we use the same values. We can forget about the global offset and the user bias because we're comparing results for the same user. And that's the output of the recommendation stage. Okay, so the results of this model are shown here. As you may remember, the AUC in the VisRec baseline was 0.6, but this model performed really well, 0.77. So it's a great improvement. And also the metrics at 100, like recall precision and NDCG at 100, improved a lot compared to VisRec. Okay, so here are the references of the models I have shown, and now we can go to a small hands-on section. I'll need to stop sharing for a sec. Okay, so this is the evaluation Jupyter notebook that you can find in the collab notebooks folder in our repository. And we have, well, first we need to download some of the files. I won't be using all of those, so give me a second. We're gonna be using the visual Bpr checkpoint. We won't be using this one and this one. Okay. So this Jupyter notebook shows the evaluation stage. What we're doing here is downloading an already trained checkpoint of the visual Bpr model. So we'll see how the Jupyter notebook calculates the metrics. And also at the end of the notebooks, we can generate some predictions to explore how well our model performs. So we need to execute these cells. The first one downloads some of the required files. Then we move to this folder to don't have any problems while importing the libraries. Here is an important cell because this cell allows us to choose which model we want to evaluate. So in this case, we want to evaluate the visual Bpr model. And that's all that we need to change. So as you can see, this same Jupyter notebook can be used with any of the models that we'll be showing you today. So I won't explain all the details of the code because you'll be seeing this one again. But here we are loading the checkpoints. Here we're setting a random seed, so we should be seeing the same results. In this cell, we're loading the embedding from the NumPy file. Yes. In this cell, we're loading the evaluation file that I showed in the first part of the presentation. So this is what our file looks like now. As I mentioned, it has the user ID, the item to predict or the ground truth, the timestamp, and the profile or the items already consumed. Okay, this cell does a lot of work. It first defines a device object, which represents, in our case, a GPU. Something important, we'll now be using a GPU. So if your code goes really slow, you need to make sure that you're using a GPU. You can do that going to runtime, change runtime type, GPU. Okay, so we define our device to represent our GPU. We load the checkpoint, and here we instantiate our model. So in our case, we're using the visual Bpr. So these are the arguments that our model uses. It's all documented in the model implementation in the file that I showed you in the presentation. And now we change the mode to eval to avoid letting PyTorch to store the gradients of the layers. And this cell creates empty torch tensors because we'll be storing all our results in our GPU, so our code can run faster in terms of performance. This additional cell may be needed in some of the models. What we do here is pre-calculate some of the values that won't be changing in our models during the inference time. So by creating by adding some pre-calculation, we can help our models to evaluate faster. And here is the evaluation loop that I already showed in the presentation. Here we generate the recommendation or calculate the scores for all of the items. In our case, we're using Visual Bpr. Then we sort those items and generate the ranking, and we use the metrics functions to calculate the metrics that of our model. And here we print those values using the mean, because we're calculating the metrics for each of our users. So the metrics over the dataset is the average of those values. And these values should be the same that you can see in our README, in our repository, and that I already showed in the presentation. This last cell allow us to inspect or explore some of our results. So here, we only change that variable. We can choose any of the rows in the evaluation file. So for example, I'm using the second one, or number one. What's the output? Well, the output is a table showing the value for each of the metrics that I already explained. And we can also see the items. So for example, this user consumed these 10 items. This is the recommendation list. For that user, we recommend 20 items. And what you're seeing here is a ground truth item, which means that the user actually consumed this item. So we recommending really well. In fact, yes, that's the only item that the user consumed in this test set. So we're okay. You can change the value and explore a bit the users of the dataset. So for example, I'm going to show now the 10th row. The user consumed these items. These are the recommendations. And this is the ground truth. Okay, so in fact, you can actually find similarities between the recommended items and the consumed items. So for example, this user liked flowers or something with a spiral form. And we have something with the spiral form. We have a couple of flowers down here. We also have horses. We have horses here. Water or coastlines, water coastlines. So it seems,
Antonio?
Yeah?
It looks like we are running a bit out of time. So
Yeah.
I don't know if you had something else to show, because the same type of example is going to be addressed by the other methods too.
Oh yes, that was all my part. So I'm okay. I'm done.
Yeah, we have just one question from Luis. He's saying, do you consider if a single item is consumed many times? Is that the case?
Well, that depends of the nature of the dataset, but in terms of the tributes that we generated, we repeat the positive items multiple times, so we can enforce that the user liked that item and that item is positive, that a lot of negative items. So
I think that Luis is talking about calculating the metrics. Let's say that you want to calculate NDCG, right, or AUC. Are you considering that the user, for instance, he liked the same item twice, or he's actually saying like assigning a weight before training? I know he's actually talking about training. Looks like. Luis, if you want, you can open the microphone. By the way.
Hi everyone. First of all,
Hi.
great talk. You guys are doing great. It's really interesting work.
Thank you. Thank you.
Yeah. So my question was about, so for example, someone is consuming the same item many times, or maybe you have a group of people. So instead of having individuals, having a group of people that keep on consuming a single item. So I don't know if you have any pre-processing of assigning it like a normalized weight even before it goes through all of the training process.
Well, at least in this model implementation, I think that that case is not addressed. And well, yeah, so if the user consumes the same item multiple times, I think it doesn't make a difference in the prediction formula. But I know that one of the models that you'll see later, that case actually does make a difference in the model prediction. So at least in this item, I think that in this model, I think that that case is not covered, but one of the models that you'll see later covers that case.
All right, thank you.
Okay, now we're starting with the next session. We're going to have a short break of 5 minutes. So go get some water, maybe a coffee. And next, Patricio is presenting. He's going to start with dynamic Bpr, a very interesting method because in this one, we are just using the embedding from a pre-trained model, but maybe we can do something else. And Patricio is going to tell us about those details. Okay, let's see you in 5 minutes. Patricio, so you can just start. I'll start the recording.
I think it's already recording, but thank you.
Yeah, great.
Oh, actually, there's a question. Oh, no. Okay. All right. So welcome to the second part of the tutorial, where we will be taking a closer look at some of the additional models, apart from, VisRec and Bpr. As Dennis mentioned, my name is Patricio Cerda. I am a machine learning engineer at MindsDB, where we work on auto machine learning. Not really related to recommendation just yet, but I am also part of the HAI Vis group. So I'll be presenting to you today, one second, this paper, Visually Aware Fashion Recommendation and Design with Generative Image Models, which is also known as DB-Bpr, for Deep Visually Aware Bayesian Personalized Ranking. This paper was accepted at the International Conference on Data Mining in the year 2017, which by deep learning standards might sound just a little bit old, but it turns out the method is quite powerful and the framework is very sound. So we decided to bring this as a natural continuation of Bpr for the tutorial. Authors are from Adobe Research and from Professor Macaulay's lab at University of California, San Diego. And in a very general sense, what the paper proposes is a method for recommending, but also a method for actually designing new elements to recommend to a user. And this is achieved through generative adversarial networks, known as GANs. But as this tutorial is focused on recommending, we won't really be taking a closer look at this second part. So if you're interested on that, I would encourage you to check out the paper and their original implementation, which considers generative or generating items. So for today's agenda, I'll be taking a closer look at the actual method that the paper proposes, and then we'll do a very quick hands-on so that you guys can see how to use the model once trained, and also like how to train it on your own machines. So this figure on the right shows at a glance what the model is about. What I was telling you, basically we have two legs to the paper. So up here in the upper half, you can see that if a user has shown interest in a purple dress before, and this can be done through some positive interaction, right? The recommender system in this case will retrieve existing clothing. So the paper is focused on the fashion domain, and it will suggest clothing that the model thinks would be interesting for the user. Now, on the other hand, there's also the personalized fashion design bit where it synthesizes new clothing that the model thinks the user might be interested in, even though it doesn't really exist, but it can be helpful for designers or store owners to get a notion of what's actually of what actually users might prefer, even though you don't have it in stock. So as I was mentioning, the context for the paper, the recommendations that it makes are in the fashion domain, which is complex for several reasons. Here we have three of them. To start off, there's a long tail distribution for fashion because you do have a lot of possible items, and every person might have a very different taste for clothing, for fashion, right? On the other hand, we also have cold starts because people that are new to your fashion portal might come in and you don't really know anything about their preferences. And also you might introduce like all the time new items of clothing that at the start you don't really know how users will interact with it, like whether will it be popular or not. And then there's also the topic of what's actually fashionable, which changes season by season, and it's actually very hard to even define for the designers themselves what's fashionable or not. So there's also there a notion of evolving dynamics. So the authors argue that having a content-aware recommender system for this domain would be appropriate because it can pick up on stuff like texture, color, shape, which might be fundamental to actually recommending the right stuff. And the key insight of this paper, as compared to VVPR, which Antonio presented, is that we opt to have domain-aware visual embeddings instead of a single, or rather an off-the-shelf pre-trained embedding for your images that belong to your items. The way to do this is to jointly train both your model that generates the visual embeddings and the recommender system itself, with the aim, of course, of recommending new items that are consistent with each user's preference. This paper uses the Bpr framework, which we have already seen. So the idea is to optimize the rank of the items that the user has interacted with in the past, and we assume the interaction to be of a positive nature. So if the user saw or liked or bought a certain item, that's positive. If he hasn't really interacted with an item, we assume it's a negative feedback. So that's the inside of Bpr, and we use the framework to train this model. Now, the visual part of the model, which generates the embeddings for your images, is said to be a Siamese convolutional neural network. This is because we contrast a pair of images, one for a positive item, one for a negative item, and when they pass through the convolutional neural network, the weights of this model are shared for both positive and negative images. And then we do the training loop. We pass the gradients. We use the optimizer, right, propagating the loss backwards. But in the moment that each pair of items passes through the CNN, the weights are actually shared, and that's why it's called a Siamese trainable CNN formulation. A very quick aside, in the data loader itself, we now need to retrieve the image instead of just passing a pre-trained embedding, which makes it be a little bit more expensive to train because we have to go and fetch the image, perform some sort of transformations. For example, if your images are not rescaled to the appropriate size, you do need to take that into consideration, and it's kind of expensive. So it's an important detail to have in mind. Even though we will be using in this tutorial the Wikimedia Commons dataset, the original dataset that the authors use in the paper are the Amazon Fashion ones and the TradeC dataset, which is some sort of crowd-funded platform for fashion. Just to recap what Antonio has already explained, we have a set of users, a set of items, and for each user, we have a set of items that he interacted with, and we assume this is a positive feedback. The image for each item will be represented as x sub I, and then we have the equation to get the ranking for each user for each item. Having a closer look at both of these, you can see that really the only term that changes is the last one here, where, and to recap, for Bpr, we have an item bias. We have the latent factors that do not belong to your visual dimension. So anything that has to do with the collaborative filtering itself and basically patterns in behavior for both the user and for some sort of description of your item will be captured in these learnable representations. And then you have an item for the visual factors, which for Bpr consists of your pre-trained embeddings in the f sub I term, a matrix that might change the dimension of your embedding, and then multiplies it with the visual factors of your user. In Bpr's case, the only thing that changes really is that we now train a CNN to develop a domain-aware embedding of your image. And the output of your CNN will be a vector that has the appropriate length so that when you multiply it by the visual factors of your user, you can contribute this term with the rest of the score for the rank of the item for a certain user. Now, a very interesting detail here is that in the original paper, authors argue that the latent factors, which they denote with the gamma sub u, gamma sub I term, they don't really use it because they argue that the CNN architecture is powerful enough to capture every sort of interaction between the item and the user. However, in our experiments for the Wikimedia dataset, this term is crucial. We need it so that the model actually learns to rank. So we are going to be keeping this term. As for the CNN itself, we use Alexnet, which Dennis introduced. And the only difference is that, say, for instance, you take a pre-trained Alexnet on ImageNet, your final layer will have the amount of classes on ImageNet, which is 1,000. In this case, we replace that final layer with a layer that has k dimensions, which is the length of your user visual factors. So we use k equals 100 for the Alexnet architecture. And it's important to note that the paper uses CNNF as a CNN architecture with k equals 50. Now, the reason they use CNNF is they argue for efficiency. So really, the CNNF architecture is a little bit smaller in the amount of trainable weights, and it trains faster. However, in our experiments, we used the Torch Vision included Alexnet, and it trained even a little bit faster than CNNF, which is also included if you want to try it out. But our recommendation here is to stay with Alexnet because it produces good results, and it trains a little bit faster than CNNF. Just to go through the Bpr optimization once more, we have a set of triples called D. Each triple has a user, U. It has an item I for which he interacted positively, and then an item J that is not in the included set of It's in the difference between the total amount of items you have and the ones that the user interacted with. And then what we maximize is this loss function. We sum over all triples the difference in the score between your positive and your negative item for the user. So this term x sub uij basically says how much more the model scores the positive item than the negative item. And we want this distance to be big, right? So we take then over this difference, we apply the sigmoid and then a logarithm. And this term here is a regularization factor so that your model has weights which are less prone to overfitting. So that's the function we optimize in this case. Now to recommend, as Antonio said, we take over the space of classes, which in this case has a sub C index here, which really only means you can possibly add categories to your data set. So you can have, in the case of Wikimedia, you can have images about, say, landscapes or people, portraits. You can do that additional disaggregation in your data set, and then you can discriminate through those classes to do like a category-aware recommendation. But really, when you go retrieve something, you just look for the image that has the item, really, that has an image and latent factors that are the maximum score for that user. Regarding the actual training of the model, we can, at least in our experience, we can see the model converges after 5 epochs of training, which is around 12 hours of GPU time using a GTX 1080 Ti and an 8-core CPU. So it could definitely be worse. There are models that are more expensive, but considering the ones that we show in this tutorial, this is by far the most expensive one to train on an epoch by epoch basis. And yeah, as I mentioned previously, the latent factors are crucial for the model to learn, so don't drop them. Either you won't get a useful recommender here. Just to quickly compare the difference between Wikimedia dataset and the ones considered in the original paper, we can see that we have less users and less items. The number of interactions is also slightly lower, but the crucial difference here is that the interactions in Wikimedia are related to the image quality because we're sort of curating each image for Wikipedia. So not really related to the actual taste of a person in the images they see. So that's a very important distinction to have in mind. Now to go very quickly through the implementation details, I think we have enough time. This is the class itself for the Bpr. And so here you will note that we can either opt for using the CNNF architecture or using the Alexnet architecture, which really comes directly from Torch Vision. And we don't pre-train because, remember, we're developing domain-aware embeddings. This two lines of code replace the final layer in Alexnet to have the appropriate K dimension. And then we define the learnable weights for your visual term or visual preference in the users, and the latent factors for both users and items.
So one question, Patricio.
Yeah.
In that slide, the previous slide, if you want to add a different convolutional neural network, it's just like adding another else there, right?
Precisely. Yeah.
Or if, yeah. Okay, yeah.
It is. Yeah, I will mention later like what the constraints are, but
okay.
It's in essence that's correct. For the forward pass, if you recall Antonio's slide on Bpr, it's basically the same. The only difference here is that we're actually applying the CNN model over the image of the item instead of going to an embedding table and retrieving the pre-trained embedding. So that's basically the only difference. And note that we return both the positive and the negative score for each pair of images. Then when it's time to optimize at training time, Both scores are the output of calling your model with the appropriate parameters. The final, like the difference is the value that is passed into the loss function that we saw earlier. And then we add, in this line, we add the model's weights so that we can add the L2 loss and regularize the model to avoid overfitting. So fairly standard optimization loop. And to recommend, same idea as in the forward pass, only that this time we receive a single item. And so for the user that you're considering, you just develop or compute that single score and return it so that you can compare for each user and each item what are the most recommended ones. As for main results, I won't really delve very deep into this. Just know that the AUC score is 0.83, which is a better AUC than in both Tradesy and Amazon. This indicates that the model is able to cope with a domain shift because we're not really in fashion anymore. We're in generic images, right? And it still performs well. And actually, out of the 4 architectures presented in the tutorial, I believe this is the one that performs the best, not by much, but it's consistent with what the paper says and what we expect. Basically, developing domain-aware embeddings is very useful. So here are a couple of examples of recommendations for a certain user that consumed these 10 images. We have these 20 recommendations, and you can see there are some, say, animals, right? And the recommendations have some sort of, this is actually like the GNU icon, but see that the actual ground truth, the recommended image is there. And also we have some fruits that are recommended and landscapes with, say, rivers or mountains, and there's also some of that as well. So it certainly makes sense. Here's a second example where we also have more like sculptures or fossils or yeah, stuff like black and white pictures. And there are some, well, this isn't really a sculpture, but this one, for example, or fossils of some sort. So it definitely makes sense. Like the learned embeddings are enough for recommendations to be quite good. So the conclusions that we get out of this paper is that, and actually the paper applied to the context of our tutorial, is that even though Wikimedia dataset is kind of different in spirit than Amazon and Tradesy, which are from fashion, the DV-Bpr model is good enough to recommend fairly well. Though, as previously mentioned, in this dataset, the collaborative filtering part seems to be more important than the content itself, or at least as important. So we think this might explain why the latent non-visual factors are crucial for the model to learn. All in all, the DV-Bpr approach is simple in formulation, in concept, yet very effective for visual recommendation in at least the fashion and the generic Wikimedia domains. And last but not least, an invitation here is to actually try out newer CNN architectures that you might be interested to explore. So for example, efficient nets, which supposedly have very good performance with an even lower computing cost, or Lambda networks, which I believe use transformers, for example, might be interesting just to see what kind of difference in the recommendations you get. Here are the references. So we have the actual paper in the first one, then there's Alexnet, and the CNNF paper. Both of those networks are included in the repository, so if you want to modify them, that's certainly possible. And now, just a very brief look at the evaluation notebook. And in the meantime, I'll be happy to take any questions if you have them.
Thanks a lot, Patricio. So you can write your questions in the chat, or you can open your microphone, no problem with that. If not, we can just continue.
Okay. So
yeah,
to be honest, it's just what I wanted to show is that the evaluation notebook is the same as the one Antonio showed. The only difference is that you have to, let me see, you have to specify that the model is DVVPR, which will trigger different behavior in all of the cells. But in particular, we're interested in seeing that to instantiate the model, you have to pass the number of users, number of items, the K dimension, right, from the checkpoint or from scratch. And this will generate here the DVPR architecture, which, as you can see, has a CNN, an Alexnet in this case. And
I have a question there, Patricio.
Yeah.
So you don't need to specify the same K size as the one used for training? That's what you said?
No, it has to be the same.
Okay.
Yeah, sorry if I misexplained, but it has to be the same for both training and then inference.
That's already specified there, right? But if you want to train, you can change it, but then you have to retrain, right?
Exactly. Yes.
Yeah.
And yeah, so the same cells. A very important part here is that if you want to test this out, you need a GPU. Like if you don't, this part of generating the cache will take a couple of hours instead of a couple of minutes. So it's key to have a GPU. And yeah, so in the last cell, as Antonio showed, you can specify a certain user ID, for example, 200, the 200th user, and it will give you a table with the relevant metrics. In this case, it's an 0.98 AUC, which is quite good. And you can see the consumed items and then the recommended items, as well as the ground truth, which is further below. It's a seagull, I think. So it got somewhere near. You can think of it. So yeah, you can test this out. You can even, if you want to train it with a different CNN, you can do so. Yeah, that's pretty much it, really. If you have any questions, let me know.
Okay, so does anyone has a question? I know that in other parts of the world it's quite late, or too early maybe. We are with more or less with the time zone, Eastern time or Central time. It must not be the same for everyone. Okay, thank you, Patricio. I think we can move on. So then we have enough time at the very end to discuss the different aspects and to conclude. And let's go with Manuel and CuratorNet. Thank you.
Yeah.
Yeah, we hear you perfect, Manuel. Thank you.
I'm gonna share my screen. Yeah. So. Welcome everyone to session 4 of the VisRec tutorial. My name is Manuel Cartagena. I'm a master's student at the Pontificia Universidad Católica de Chile. I've worked a lot in recommender systems, but my main focus is on generative models. So I'm a little bit on the other side of deep learning. And I'm going to present you CuratorNet. That is a model we developed at our research group. The main author is Pablo Messina, who is not here, but all the other authors are the ones that are presenting today, including myself. Well, CuratorNet is a visually aware recommendation of art images. Well, what is the context of this paper? It's recommendation of visual art. There are a few works in this area compared to movies or music, as you may know. And most previous work is focused on museums and cultural collections mainly. So there are a few studies about recommending paintings in a commercial setting. The other part of the context is the dataset. We work with a U-Gallery, that is an e-commerce of physical artwork. So it's a small dataset. We had like 5,000 transactions or purchases from approximately 2,000 users and they were 6,000 paintings. At your right, you can see a histogram of purchases per user, and you can see that the number of purchases per user is mainly one. It's more than 60% of the users only purchase one painting. So our problem is that we have one-of-a-kind items. So when you have physical artwork and you try to recommend a painting to someone, and the person bought it, you can't recommend the item again. So it's like there are no co-occurrence as the Bpr or Vista paper from Hea Magoli that Antonio previously showed you. And our dataset is very small compared, for example, to the YouTube dataset or the Bpr Vista, which are our main inspirations for this model. Where the idea is to address our problem is that, for example, in the YouTube paper, they do not learn an explicit user latent vector. And in the Bpr paper, they perform the training learning by sampling native feedback, which already Antonio and Patricio showed you. Well, we had an idea of what about combining visual content with clarity information without the need of an explicit user latent factor. And so we developed CuratorNet. You can see our original implementation of the model in TensorFlow 1 in this link. But for this tutorial, we developed a version in PyTorch. Well, CuratorNet is a neural network architecture for visually word recommendation art images. Well, here's the model architecture of CuratorNet. I'm going to show you step by step this model. On the first part, we have the input. We have a P subscript U, which is the user profile, all the paintings that a user bought. And from this user profile, we took one of the paintings and used it as a positive sample. And for negative sample, as Antonio said earlier, we use any painting that the user did not interact or bought. After this, we pass this to a pre-trained network. We use ResNet 50, which its output is a 2048 embedding size. And with this pre-trained embedding, we pass it to a couple of layers of shared weights, very similar to a Siamese network architecture of sizes 200 and with a scaled exponential linear unit instead of ReLU, the typical rectified linear unit. After that, for the user embedding, we use average pooling and max pooling after a few other linear layers to create the embedding for the user profile. And with all these embeddings learned, we calculate our loss. And pretty much like Bpr, we have a prediction score where here phi is our model, P subscript U is the user profile, and Fi are the images. So we want to have a high score for the positive image and a low score for the negative image. Well, how does this transfer to code? Here are a couple of screenshots of our repository. For example, the model is in the folder models, and the file is curatornet.py. Well, here is the class curatornet, which is a Python class that inherits from the PyTorch neural network module. And in the initialization, we define an embedding layer from pre-trained because we use the pre-trained embeddings. And you can see in the forward pass that this is used for the profile, where we load the embedding from the user profile for the positive image and for the negative image. After that, we have the common section, which I already told you. There are a couple layers, linear layers with a CELU activation. And you can see that as in a Siamese network, there are the shared weights that we use for the positive item, for the negative one, and for the user profile. And finally, we have the profile section specifically for the user, where we use max and average pooling. And after that, we pass it to some linear layers, also with a CELU activation. And you can see here that we concatenate these outputs of the max and average pooling, and we pass it to the linear layers. And finally, in the forward pass, we calculate this X subscript UI and X subscript UJ. That is for the user positive image and the user negative image. And we pass the difference to as the output. Well, what is the loss function that we use? We use a sigmoid cross entropy loss. I already defined all these terms, so it will be easy to understand. First, we have the class. That is, we have two classes: 0 that is wrongly ranked, and 1 if the items are correctly ranked. Here we have the term for probability that the user U prefers the item I over J. Sigma here is the sigmoid function, which you can see down here. And we also add the other probability that the user U doesn't prefer the item I over J. And finally, we add a regularization hyperparameter. We use the L2 norm. Well, in code, the loss function, you can see it in the training procedure IPython notebook. In the training setup, you can see that the optimizer, the weight decay parameter is the L2 regularization. And for the criterion, we use binary cross entropy with logits. I added a link that you can see that in PyTorch, the sigmoid cross entropy is really this class. Well, and how do you train this model? It's very similar to Bpr, that given a training set D subscript S of triples P, I, and J, where P is the profile, I is the positive image, and J is the negative one. We aim that our model score is higher for the positive image than for the negative image. And unlike Bpr, here in CuratorNet, we do not randomly sample the negative examples for the training of the triples. We use different sampling guidelines based on previous work that we did, where we looked at the favorite artist is one of the most useful things for sampling in this setting, but also we use the notion of visual clusters. And you can see here examples of visual clusters that were automatically generated for sampling. And you can see that they are very good clusters. So you can see images very similar are in the same cluster. And we also studied what is the effect of these sampling guidelines. And you can see in this graphic that for AUC in CuratorNet and Bpr, which Antonio presented, using the guided sampling, we have a significant improvement over AUC. Rather than using random sampling or naive sampling, as someone also called it. Well, now, how do you make a recommendation? Previously, Antonio showed that for VisRec, this is the setting where you calculate a score based on the profile of the user and the content. But now, we use the user model representation by CuratorNet, and also the representation of the items made by CuratorNet, and we calculate the score and recommend using maximum similarity. Here are the results in the Wikimedia in the Wikimedia dataset. They are not as good as other methods. We have an AUC of 0.66, almost 67, but one important aspect is that CuratorNet does not explicitly use the collaborative filtering information. We use it inherently in the user profile that we learned from the items embeddings. So, for example, in uGallery, with the guidelines, we have an AUC of 0.72. Well, here are the references. We used our main paper that was presented at Rexis, Bpr, the YouTube method, and well, Bpr and else. And for hands-on, I'm going to show you. Well, it's the same notebook as earlier. I know, I can show you like step by step. In this cell, we download the data, as previously said by everyone. This this step is
So
important.
one second there, Manuel. There at the very top. So usually you uncomment all the methods excepting the one that you're going to use, right?
Yeah, here we made the collab notebook so that you can download all the checkpoints we made.
Yeah.
So for example, if I only want the curator.net one, I can comment these lines. But you can download every checkpoint and every data that we need to use all the methods on the same notebook.
Okay.
There's no problem with that. One of the important things to do is to move to the main folder of the repository, so the imports work. And in the evaluation procedure, we specify that we're using curator.net for this example. And in curator.net, there's the profile mode because we gather profiles of the same size in the evaluation loop, so it will be easier to store it in the GPU. After that, where here define all the paths for the files, for the checkpoints and the data, we freeze the RNG seed, so we get the same results over and over. We load our embedding file from ResNet 50 in this example. And we load the evaluation data frame, which you can see there, the same as Antonio showed. We have user ID, the item to predict.
Manuel?
Yep.
Your screencast is a bit behind, lagging your voice. So try to move your mouse a bit more slowly.
Okay. Yeah. So we have the evaluation data frame, user ID, the item to predict, the timestamp of the purchase, of the interaction, and the profile, which are all the items that the user interacted with. After that, as Patricio showed, we initialize the device, in this case a GPU. We load our checkpoint and we initialize our model, in this case curator.net. The curator.net only needs to receive the input size of the pre-trained embedding. In this case is 2048 for ResNet 50. After that, we load the checkpoint to our model and we change it to evaluation mode. And after that, we use the same setting as everyone. And in the evaluation loop, we show the metrics that we obtain, and there's in our README and in my slides, which is 0.6669 in AUC, which is better than VisRec, but not as good as the other methods that we showed. But if you go to the user inspection, you can see that our recommendations are not that bad as you might think by the AUC. For example, for this user that consumed 10 items, you can see landscapes, birds, cars, and in the recommendation you see all that. You see some birds, you see some landscapes, you see also cars, and the ground truth was like a landscape of snow, but our model ranked it in this 106th place, which is not that bad, considering that we do not use the collaborative filtering information explicitly on our model. If we check another user, we can see that this user interacted with a lot of animal pictures, and you can see there are some flies, some cats or tigers in this case, and you can see that
Feline at least, right?
yeah, the recommendations are good, but because Wikimedia is more like a quality of image dataset, for example, the ground truth is something that you don't see any in the consumed items. So using only the visual aspect of the model, it's difficult to recommend this picture. But in other settings, this model is really good, and as you can see for the results in your gallery. And one of the key aspects that you need to learn from CuratorNet is that we do not we learn a user representation only based on the items. So for example, if a new user comes to your platform and you want to make recommendations, you don't need to retrain your model to make recommendations for that user. You only use the items that the user interacted with. And I think that's one of the strong points from our model. And you can see that the recommendations are not that bad. I don't know if there are any questions in the chat. I'm looking at it, but
I don't see any questions. We are good on time, so I guess we can move to Felipe.
Yeah.
Let me pause the recording.
So my name is Felipe del Rio. I'm a PhD student also in Pontificia Universidad Católica from Chile too. I usually work with systematicity in deep learning models, but right now I'm going to present you ACF. So ACFs come from attentive collaborative filtering. The original paper is called Attentive Collaborative Filtering, Multimedia Recommendations with Items and Component Level Attention. This was presented on CIR 2017, and you can see the buzzword attention, which comes from the same year from the paper Attention Solve Units. So it was quite contemporary to that paper. So a little bit before all the attention revolution started. At least the big attention revolution, because before that it was quite important in sequence-to-sequence model too. So this is a nice implementation of one kind of way of applying attention. The contents for this paper is multimedia recommendation. In this paper, they focus that multimedia recommendation usually doesn't have a large amounts of explicit feedback. When you watch YouTube, you don't have the chance to put 5 stars on the video. You put like or dislike at most. Also, but you can also give feedback to the system by playing the video, or when you go to Spotify, you can play the songs, or in Facebook, you can, or Instagram, you can like the pictures more than actually rate them. So it's important to so the authors focus on this kind of implicit interactions. The two key insights that build these models are first, there are 2 levels of implicit feedback. Traditional content-based collaborative filter models, they focus mostly on the item as a whole, while when we are working with multimedia kind of items, the parts of the items are much more are semantically richer than just an ID. So we can leverage those parts, like parts of images or parts of the video or parts of the song. So somebody might like to see a basketball video just for the scores that they can see, you can see on the video, and not the whole basketball video or the best plays, and that's not reflected in traditional content-based collaborative filtering. And the second important insight for this paper was to leverage an annotation mechanism that in this case would be hierarchical because of what we said earlier, to weight the different parts of the different parts that are going to be taken into consideration when providing a score or a recommendation. Instead of traditional ways of weighting, these kind of things like average weighting, this can be used adaptatively and leverage this idea. So the approach, like I say, they focus on implicit domain. So they use a Bpr style based training as the other method we have seen before. But importantly, they use a mixture of a latent factor model with a neighborhood model for the user, for the representation of, especially the user. We're going to see it a little bit deeper in a second, but this combination makes that the user is not going to be only represented as a latent factor, but it's going to be also enriched with the profile of the items that that user has already consumed. The original paper was tested on the Pinterest and Vine dataset, but in this tutorial we're going to focus on the Wikimedia dataset, which we have presented so far with all of our methods. So let's start building the model from the ground up. So for this model, we need three things. First, a user, an item, and a component representation. We're going to work with user I, and we're going to represent it by its latent factors. It is like a vector UI. And this is one part of the model. We're going to keep building it, one of the part of the representation of the user, but it's the first part, and this is the latent factor part. And we're going to build it a little bit. We're going to see the other part in a moment. The items are going to are also going to be built as latent factors. We're going to have vectors B sub j and P sub L. They both, it's important to notice that they both might represent the same user, as the same item, sorry. The only difference between them is that they are used in different contexts. When we use the B subscript J, we refer to the item that we want to score, while when we use P subscript L, we represent the item that's going to be that's going to help to characterize the user. You can use different kinds of embeddings for these vectors. For this, this item, maybe the same item can have two different kinds of embedding, but in this case, I mean, in this implementation at least, which is a little bit different from the original one, we tied that so that the representation is the same for both, and this makes it a little bit more efficient. We need less memory in the GPU, and have a little bit better performance. And the last part, of which I will go deeper also in a moment, but I want to set the notation a little bit from here because it's going to appear right away. It's when we talk about component M of an item L, which you can picture it as a region of an image or a sequence of frames of a video or a sequence of a sequence of text from like one sentence from a paragraph. It's going to be the part M from item L, and we're going to make the notation with this X subscript LM. So we have the latent factor representation of the items and the user, but we want to create a richer representation for the user. And this we're going to do it by summing up the latent factors vector for the user that we have before, that's going to be learned here, with the profile, which is the representation of the item in the profile. And how are we going to weight it? We're going to use an item level attention. This is the first attention that we're going to use. As I told you, we have this hierarchy of attention, and this is the top hierarchy. And we'll see how do we build this, but you just have to know that this is going to weight the different items instead of just averaging them, and as it would be like more straightforward to just do it. So with this representation, we just score each item in the same way as we do it in any latent factor model, which is just the dot product between the user and the item. Just implementation detail for this tutorial, we limit the maximum number of the profile to 9 per user because of term efficiency, and because if you did larger, the training would be much inefficiency because of there will be an increase in the paddings, which are these like blank tokens, and it won't. It would be much more inefficient actually. So how do we do this in the code? So this is a hands-on tutorial. We want to share. It's going to be sharing how do we translate this into PyTorch code. So for a model ACF, we have the class ACF, which is like the top domain. They like the top hierarchy part of this model. It keeps it stores the user, the items, and also it has a user representation net that is here, as well as the item embedding model. This embedding layer stores all the factors for every item. The important method that you have to take in consideration when using this ACF class is first the forward pass, that is going to be used for training. So it gets the user ID and the profile ID for the user, as well as the positive and the negative item. We have also a profile mask, since the profile is variable length with some profiles, and we're going to train it in a batch. Some profiles are going to be larger than the other ones in the batch, so we want to mask those items that are not going to be used. So that we don't introduce noise to our model. And it's pretty straightforward. So we get the user representation from here, from the user model, and we get the prediction for the positive and the negative. And the prediction just means that we're going to get the item factors and make and score it by making the dot product between the item and the user. The alpha term that we see before is the first level of attention that we're going to see, and this is can be interpreted as how much attention I'm going to put for that user. So going to place for that user into that item of the profile. So I might have a user that focuses on faces and birds, and maybe he always picks faces when being recommended. So you should put more weight on those kind of examples. And what do we do? What do we take in consideration for creating this attention? First of all, the factors of the user. We also include the factors of the items that are going to be represented. In this case, since we're going to use the same representation for the items in both when scoring and when in the profile, this term is redundant. And finally, we're going to use the representation of the item as built from its components. And this is the second layer of attention that we're going to see in a moment, before I show you the code for this part. But you have to, in the same way that we're representing a user from his profile by weighting them differently each item, we're going to weight different parts of each item. You can think about it as different regions of the image. Maybe if you have a face in the image, that part of the face, it's more important for someone, or maybe someone, when you have a face on the image, you can focus, he focuses more on the eyes, and other people focuses more on the smile. But we are going to have a summary for each image by weighting them, and by weighting its components and creating one vector from this attention. So this is what we're going to build in the next attention. Sorry. And lastly, we have to normalize this, because these are just numbers and there's no constraints, so the sum is normalized. And we're going to do this as most attention using a softmax function. And how do we implement this in PyTorch? So we have the ACF usernet, which is, we have the task of creating the user representation. The important things to know is, well, it has all the linear layers that are going to be used. But as well, they have also the embedding layer for the user, for the profile, sorry, which can be shared with the user if this is not defined. This profile embedding is not given to it when creating. It has the embedding the user latent factors here, and it has the feature net, which is the ACF feature net, which we're going to see right after this, which has the task to compute the representation of each item as a weighted sum of its components. When we when we do the forward pass for this usernet, the important steps are first getting the latent factors both from the item and the user. Then we're going to get the weighted representation of the item as part of its component. Then we have to create the attention, and this piece of code is going to create these alpha values here, and it's going to ponder them and sum them to create the user profile part. And finally, it's going to add this representation of the from the items to the user to enrich this user representation. The component part of this model, which to me, I think it's one of the most interesting parts. There's one key difference from the models that we've seen before, and for me it's important to notice this, because when so far every model that we have seen, we have passed an image through a convolutional neural network and keep the last layer before classification. So this layer is, in the case of our ResNet 50 that I'm showing here, it has the dimension of 2048. But since we don't want to aggregate all this information in this kind of models, we want to have we want to keep the spatial information from the image. We want a mix from the semantic information to the spatial information, and in this layer we eliminate all this spatial information. So we want to go one step further, one step backward, to a layer that still has some of the spatial information. And at the ends of every convolutional neural layer, you have this, the results of these layers are always in this kind of cube. So in the case of ResNet 50, it's going to be 7 by 7 by 2048. And you have to, and you understand it, like, and each of those vectors, the 7 by 7 vector is going to represent a different part of the image. So one of these vectors is going to be represent the smile, another one is going to be represent this part of the image, the eyes. And when we average pull them, we lose all this information we would like to share. And for this is what we're going to do, use attention. In the case of this tutorial, I used the ResNet 50 layer 4, the output of the layer 4, which is right after the average pulling operation. And because the vectors, the dimensionality of the vectors is quite large, 2048, I immediately reduce this dimensionality to something that is more manageable. You can still work with 2048, but I think to learn, it's a good idea to just put a linear layer there that is going to be learned, and it should learn what information is important for our task, which is recommended. So when you pass through that layer, it's going to be the result is going to be something about it's going to be 7 by 7 by 128, which is much more manual. So when each of these vectors, which is 7 by 7 by 128, is what we have here, and we want to compute another attention that's going to weight these vectors so we can average them. And this is going to be this beta over here. This is much simpler than, it has the same structure, but it's a little bit simpler than the alpha that we computed before. It takes into consideration the user factors and the components of that item only. So if the user likes smiles, this should be higher in value when here we have a smile. If the user likes eyes, here is going to be, this whole sum is going to be higher in value when the user have see eyes that he should like. And well, it's an attention, so we pass it to a softmax, so it's normalized. This is implemented in the same ACF .py in the model directory in the class ACF FeatureNet, which has this logic, component level logic. And as you can see, the first part is to reduce the dimensionality of the components. Then we're going to compute the attention, which has the same structure as before. And finally, here, in the last line, you're going to sum and return the components. We're going to use a Bpr optimization objective. Like optimization objective, actually, it's a word loss, which is one step further in the road, and using training Adam, which is like a good optimization algorithm for training neural networks. One important thing that we how do you say, when we implemented this model, we had the issue at the beginning that our attention were coming out flat. I thought at the beginning it was a bug from the model, but it's important that regularization was key to actually avoid this flat attention. So if you implement it, I would suggest to put some effort on seeing which lambda works better for you. For us, 10 to the minus 4 was greater than 0, and less than 10 to the minus 4 were good, and 10 to the power of minus 5 achieved the best results for the values that we test. Well, the trainer, we give you a class for this, so you can use. It has the optimization loop, the train and eval and val phase. And the base of the training is in the training step, in which you're going to get the inputs and pass it in the forward pass and then a backward pass. It's important that we have parameterized the loss, so it's pretty easy to test new loss. And you can test here the Bpr loss and the verb loss. We use the latter for this tutorial and for building this checkpoint. We get quite good results. We're the second best model from this tutorial, but as in AOC, so I think this method is pretty solid. So I'm going to go to the collab. I don't know if you are going. Are you seeing the collab or the slides?
So far, we are seeing the slides, Felipe.
Same evaluate evaluation notebook that you've seen before, thrice actually. So I will go directly to the interesting part. You go here, you can see actually the values that are in the GitHub and the slides that I just presented you, as well as the inspection of items. Here I pick an, so you can see the recommendations that this model consume.
I think you're not sharing screen, Felipe. I'm not sure.
Yeah, I'm not seeing your screen yet, Felipe.
Here?
Now we do. Okay.
Okay. sorry for that. Okay, so as I was telling you before, this is the same notebook as before. So just jumping into the a little bit more interesting parts. Well, first is the summary of metrics that we get for training this model, and there are some recommendations in the way that this model produced. In the same as before, actually I think this is an example that, or pretty similar to what Manuel showed. And this is, here you can see like this user likes snow and views of cities and kind of views, and you can see lots of scenes here, like here, and here in the recommendations. So it looks quite accurate. But one of the no, this is what I didn't want that to happen. Well, one of the things that is most interesting from this model that sets it apart is its ability to leverage attention. So, and something nice about attention is that it's easily you can easily visualize it. So if and when you visualize it, you can have a better understanding of what is important for this model. So remember that we have two levels of attention. First is the profile attention. So when I am representing a user, I will weight each of the items it's already consumed. And in this case, we can visualize how this model leverage this profile attention and puts all the attention in this item. So this is the profile from the user. And I don't know if you can see, I want to increase a little bit the value so you can see a little bit better. Here is the amount that, how much did the model weight that image to make the recommendation.
So it seems like the model is paying a lot of attention to the sky.
Yeah, to make a
because
lot of
the other ones that have at least non-zero attention, all of them have some sky there, blue skies.
Yeah, yeah, and you can see it makes some recommendations that are pretty similar to that sky actually. Here with clouds. The actually ground truth was how do you say
a deer?
A deer, yeah. And the other part of the attention, which is, in my opinion, a little bit more interesting or a little bit more visual, appealing visually, is that you also have the attentions from the different regions of the item. So you can actually see that the model is actually attending to the objects usually from the images. That is not the case in every image, but it's pretty impressive that here is putting attention to the ostrich. Here is putting attention to the person that appears in this image. Well, this is something that I don't know, but here is putting attention to the hand. I want to show you maybe another example. If I didn't have the bad luck to miss this session. Yeah. Just to be, this notebook is inspired on the evaluation notebook, so the way to use it is pretty straightforward. It's the same way. The same, you have to use it in the same manner. The only difference that you can only use it with this model or a model that if you want to add it, it has to have attention, so you can actually visualize it. So this is the same one.
You're trying to change the user?
Yeah. I don't know a way to.
Yeah, it up there says save fail. I hope that has issues only saving, but not on the output of the.
Yeah.
Let's
Yeah,
see.
because no, here is different.
Okay.
Okay. So here we have another item, another user. You can see that the user the model focuses most on this image for the recommendation. This is here we have seen that the attentions are really spiky. So there's one that dominates the other ones, but it's not that the case in every time. It's just that the ones that I wanted to show that are not like that are not didn't work, but it's not that you can have like 30% sometimes. You can see that it happens both ways actually. So here, like you see, and it has a lot of attention also in this, like in skies with clouds, and here it also have puts recommends some images also with sky and clouds, as well as, and here you can see where it puts the attention in the images again, and you can see it can put it on the building. Here it put it on the persons, on the lettuce, the owl.
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 Yeah.
Yeah. As well as parts of the building too. So this you can leverage. The attention mechanism is interesting because you can actually leverage to have some idea of what the model is looking for in the image, and maybe not only help you debug it, but in the same way, in parallel, also increasing the performance, as it has been shown many times by transformer like models, which are completely based on attention.
Okay, so are you done, Felipe? You need to go back to your slides or not?
No, I am done.
Okay, so I think that we are pretty good on time, and we are just good to close the session. Let me go to the slides if I find them. Session. Okay. So I really appreciate all the people who started until the very end, because it's been a quite long tutorial, and I don't know, maybe you guys are in a not such a good time zone compared to the not good, but a very far time zone. So you are maybe very late at night or very early to watch this version. So instead, anyway, we are going to save this recording, and you will be able to then rewatch, check again the tutorials, the explanations. You will be able to see in the repository again, code, slides, data set, and we really hope that we have made a contribution with this. If you have any idea of maybe, I don't know, modifying the loss function, trying to do a different type of training, you can also send us an email. We will be really happy to collaborate, for example. We are, as Manuel said, we are not exactly always working on this, but in very related fields. So, for instance, Manuel is working in generative models, but on music. So maybe some of these we can adapt them to music domain. Antonio is working on recommendations, visual recommendation with explanation. So maybe if you have some idea, some data set, we can also find ways to collaborate. Patricio is already working, but he also is always open for collaboration, the same than Felipe. So again, we really appreciate that you stayed until the very end. We also encourage you to share our slides, our tutorial, and if you have any comment or question, please be open to feel free to speak. Erasmo and Luis. So where are you now, Erasmo and Luis?
Germany.
In Germany, wow.
Yeah.
It's quite late there. So we really thank you for staying so late there for watching our tutorial.
It's quite midnight. Yeah.
Yeah. So are you doing research in this area, in recommendation or in something related to images?
Yeah, I did. Okay, I can share my screen. Okay, this is my actual venue.
Wow, you're having a really great time.
No, I did some work in past for my master thesis on content-based image retrieval.
Yeah.
Now I'm a PhD student, but I'm working on recommended system in graph-based structure, but I'm still interested in image context. So I really
that's something very
tutorial.
interesting, actually. Yeah, that's very interesting because since apart from NLP, graph neural networks is also a very hot topic right now.
Yeah,
trying to maybe leverage information from a graph structure and combine it with collaborative filtering and with content, with visual content would be really great idea. So hopefully we will be reading your paper soon. That would be great.
I hope so. Yeah, graph neural network obviously is one of the main topic I'm studying right now.
Yeah, cool. So we also had the questions of Luis during the session. Luis, where are you now?
Well, hi everyone. I'm actually in a pretty good time zone. I'm in Texas, so no issue
perfect.
here. Like
3:30
o'clock. So we're good. We're good. So I'm from UT El Paso, on the very west side of Texas, right next to New Mexico, and we have Ciudad Juarez right below us. And yeah, well, for me, all of this topic about recommender systems is well, relatively new for me. I only started working with recommender systems by the end of last year, because we are trying to bring recommender systems to completely different domains. Our plan is like that we need to start sharing information and about models, scientific modeling, and especially here in the area where I'm at, we have a huge issues of water scarcity.
Wow.
Yeah, exactly. So
well, you know that in Chile we are also having a big problem on that, because the desert, which is in the north, is somehow advancing to the south. So here in Santiago, it used to rain a lot in winter. Now it rains very little. So every year we are having like, hey, next year we will really need to start like consuming less water and stuff like this. I didn't ever thought of Rexis applied to this field, but we are starting increasingly to see this topic of trying to take care of water. So I would really, if you have any idea on that, using recommender system to research on water scarcity or how to face it, that would be cool. We will be really happy to collaborate in that sense.
Yeah, so I can give you a brief summary of what I'm doing. Basically, well, we have this kind of complex surface water models and groundwater modeling. And the plan is that we bring different stakeholders for participatory modeling. So we try to bring in the community, water managers, farmers. So water affects everyone, but everyone has different perspectives and different views about water. So and the scientists sometimes are very focused just on the research area, right? So maybe they're kind of disconnected of the real world. So what we try to do there is that when we bring all these people in, we cannot just give them this really complex model. They don't have the software, they don't have the knowledge, and so on. So
okay, yeah.
Yeah, so my work here is to kind of build a whole cyber infrastructure so that people can interact with these complex models, but through a web interface. And since these models are so complex and have a lot of variables and outputs and so on, we want the recommender systems to help people guide them through that model, right? So for example, if you're a water manager, you probably want to see outputs from that model that have to do with your specific concerns. We don't try to pigeonhole people. We do give them the option to change their roles around, because you can have several roles, right? You can be a water manager, but I'm also a rural resident. So maybe I want to know both things. So that's kind of the why I'm interested in
yeah, I have a PhD student working on that right now from the perspective of narrative visualization. But she's studying it from a different perspective. She wants to see how information visualization can have an effect on public policy. So when you see the cycle of public policy, there is this initial step called agenda setting. And what we are studying is how much you can influence agenda setting with a nice visualization, but with different aspects, right? Maybe interactivity, maybe just illustration with information visualization, or just simple illustration. Well, that sounds very great to know that you're working on that. Probably we will find your, I don't know, your email or something. And if we can collaborate with you or Erasmo in different topics, that would be great.
Yeah, that would be great. I mean, my plan is to publish in this conference next year. We have some pretty good stuff. But yeah, definitely looking forward to it. And yeah, we're doing very similar stuff. And we also have interfaces, narrative generation, and things like that. But the recommender systems will help us answer like the what question. What do we want to show each group of stakeholders? And then through the narratives, we decide kind of how to explain those results.
Wow. Well, great topics, great challenges. We are just on time. This is not usual for Chileans. We always get late to everything. So I'm very proud.
Also for Italian, like me.
Yeah, like Latin stuff, right? we take the time a bit loosely, but
exactly, never on time.
Yeah. Okay. Take care, guys. Thank you, and we will be uploading all these recordings so you can see it later if you need it. Yeah. Bye.
Yeah, bye bye.
Thank you.
Have a great night, a great day. Yeah.
Bye.
Thank you again, guys.